Okay, so on problems we were working with before, we had ones like this. This example, we're taking this region bound by y equals x, which is going to be this line right here. Y equals x. The vertical line x equals 2. And y equals 0, which is the x-axis. And we're going to take this region and revolve it about the x-axis. And so what would happen is we'd revolve it around the x-axis as such, and we'd get this figure that looks like this. And it would be a cone. Okay? Our figure would look as such. Okay, there's our region revolved about the x-axis. And we look at a cross-section as such, you can see that it is indeed a cone. Okay, so let's look at the region bound by these functions y equals x, which is this going to be right here, y equals 2, which is a horizontal line, and x equals 0, which is the y-axis. We're looking at this region right here. But now what we're going to be doing is revolving it at about the y-axis. Okay? So what would happen is we're revolving it about this right here, y-axis. So it's going to be come around as such. Okay? So it's going to be basically like this. It's going to be a cone as well, but it's going to look like this now. It's going to look like this right here. So it is once again a cone. Okay? But it's now revolved about the y-axis, revolved about the y-axis. Okay? Okay, so to find the volume of this figure, once again, for ones like this, if we're going about the y-axis, okay, if we're going about the y-axis, if the entire region that's being revolved is touching the y-axis, then it's going to be a disk. Okay? So we're looking at, for instance, look at this region right here. The entire region is bound right here on the y-axis, revolving it around the y-axis. So therefore, we're going to be using the disk method as opposed to the washer method. We'll look at those, a couple of those in a few minutes. Okay. And so now our A and our B values are going to be, our limits of integration are going to be in respect to the y-axis. Our starting point and our end point with respect to the y-axis as opposed to the x-axis. Okay. Once again, we're going to be looking at an infinite number of disks, adding up the volume of all those. So since they're infinitely thin, we just have to worry about the area of each one of those disks. And the area of any circle is going to be pi r squared. And our radius now is going to be x. It's going to be our x value. No matter what you're talking about, our radius is going to be our x value. And we're going to be integrating with respect to the y-axis. Hence, it's going to be dy. And I'm going to show you how these little small changes are going to affect us. Okay, so let's look at this right here. So we're going to sketch this figure, and we're going to take the area revolving about the y-axis. So first off, y equals 1/2 x. So make a little sketch of this. Okay. So 1, 2, 1, 2. All right. And all right, so y equals 1/2 x. That's going to be a linear function that goes through the origin and has a slope of 1/2, rise over 1, so up 1/2. So it's going to look like this. Okay, y equals 1/2 x. Y equals 1 is a horizontal line as such. And x equals 0 is the vertical axis, vertical y-axis, which is as such. So the region that we're going to be revolving about the y-axis looks like this. Okay, so we're going to revolve this around the y-axis. All right. So it's going to be a figure that's going to look like this. It's going to be kind of a cone-looking thing, kind of like a, well, it is a cone, actually. It's going to be a cone. And so it's going to look like this. All right, so our A and our B values, our limits of integration. So first off, because the entire region is touching the y-axis and revolving about the y-axis, it's going to be a disk method. So it's going to be from A to B, the area of the disk, and it's going to be dy because we're revolving about the y-axis. So it's going to be from a to b, pi r squared dy. Okay. Now, our a and our b values are going to be with respect to the y-axis. Okay. So therefore, looking at this, we can see that we're going from 0 up to 1. This horizontal line is going to be creating our upper boundary. So we're going from 0 to 1. Now I can bring this pi out because, once again, that's just a constant. So we're going from 0 to 1. Now our radius is going to be given by x. Okay? But what was going to be, so our radius, let me write this down here. Our radius is going to be given by this function, but it's going to be our x values. So one of the big changes on this is, instead of this being going to be our radius in terms of x with dx, we're going to be using dy, so our function needs to be in terms of y. So what we do is we take our function y equals 1/2 x, and we're going to solve for x. So to get x all by itself, I'd multiply both sides by 2. So x equals 2y. Okay, so that now is going to be our radius. That is going to be our function. Y equals 1/2 x is the same as saying x equals 2y. So this is our function that we're going to be using. That is what our radius is going to be. It's going to be 2 times y. That's how far we're going to go out. That's what our radius is going to be. So we took the pi out. It's pi r squared. So our radius is 2y squared dy. And that's going to be pi from 0 to 1 of 4y squared dy. And I can take this 4 out because that's just a constant. So I have 4 pi from 0 to 1 of y squared dy. Okay. Now I can go ahead and take the antiderivative. And it's going to be 4 pi times the antiderivative of y squared is, of course, 1/3 y cubed. And I'm going from 0 to 1. Oops, not sure what's going on. Whoa! Not good. Not good. Okay. So, hopefully this will work for me now. Sorry about that. Now, this 1/3 is simply just going to be a constant as well. So I can multiply by the 4 pi to get 4/3 pi. And now I just have y cubed from 0 to 1. So I plug in 1. And I get 4/3 pi. 1 cubed minus 0 cubed, which gives me the answer of 4/3 pi units cubed. And that is our answer for that one. Sorry about that crazy pin problem I had, but I think you pretty much get the idea of what's going on. Okay, so let's go over another example. All right, so it's bound by y equals x cubed, y equals 1, y equals 8, and x equals 0. All righty, so 1, 2, 3, 4, 5, 6, 7, 8. And I know how this is going to look, so I'm not going to sit there and write these all out. But first off, and this is going to be over the y-axis, by the way. So y equals x cubed, I know that looks as such. It goes through the origin, 0, 0, over 1, up 1, over 2, up 8. So it's going to look like this. And there we go with these problems again. Let's see if I get this to work. Okay, y equals x cubed. Y equals 1 is a horizontal line at 1. Y equals 8 is a horizontal line at 8. And x equals 0. So this is my region right here that I'm going to be revolving that about the y-axis. So I'm going to have this figure that looks as such. And it's going to go from here to here. Kind of looks like a shawarma. Like if you go to a Euro place. Kind of looks like that, right? Okay, so it's going to be this figure right here. Okay, so once again, the region that we're revolving about the y-axis is all touching that, so it's going to be the disk method. So going from A to B, area of the disk. So we're going to find the volume of infinite number of disks, add them all up. That's going to give us the volume of that entire figure. So we find the area of each one of those infinitely flat disks. dy, remember, because we're doing with respect to the y-axis. And it's going to be from A to B, and the area of each one of those is pi r squared, dy. And I can bring this pi out. Now remember, my limits of integration are my starting point and my end point with respect to the y-axis. So it's going to be bound by these two horizontal lines. So we're going from 1 to 8. Now, my radius. Our function is y equals x cubed. However, we want this, since we're doing it with respect to integrating with respect to y, dy, we need these to be in terms of y. In terms of y. So I need to rewrite this as x equals whatever that's going to be. So I'm going to take the cube root of each side. I'm raising that to the 1/3 power. So I get x equals y to the 1/3. Okay? So that's what my radius is going to be. It's going to be my function, y equals x cubed, but rewritten in terms of y. So it's x equals y to the 1/3. That's what my radius is going to be no matter where we're looking at any of these disks. Okay? That's pi r squared. That's my radius. So y to the 1/3 squared dy. So I'm going to be going from 1 to 8. Pi's out here. And that's going to be y to the 2/3 power dy. Okay. So I'm going to take the antiderivative. And the antiderivative of y to the 2/3, I'm going to add 1, which is 3/3. So we'll get y to the 5/3. And I think we've done these enough times, so you know that it's simply going to be, the coefficient is going to be the reciprocal of our new exponent if there's no coefficient out here. So it's going to be 3/5. And from 1 to 8. And what I can do now is I can move that 3/5 out front. So I get 3 pi over 5. And so I'm looking at y to the 5/3 from 1 to 8. Okay? So we've done these many times, but I'm going to go ahead and do this over to the side. So if I have y to the 5/3 power, that's the same as saying y to the 1/3 to the 5th power. So I take the cube root of whatever that value is, then you raise it to the 5th power. So I'm going to plug in, I put the 3 pi over 5 out front. I'm going to have 8 to the 5/3 minus 1 to the 5/3. All right. So first off, 8 to the 5/3 is the same as saying the cube root of 8 to the 5th power. Cube root of 8 is 2 to the 5th power is 32. So 8 to the 5/3 is 32. It's going to be 3 pi over 5. 8 to the 5/3 is 32. 1, cube root of 1 is 1 to the 5th power is 1. So we get 3 pi over 5 times 31, which is 93 pi over 5 units cubed. Okay, so we're trucking along. This ain't too bad so far. And let's look at one more problem. All right. So, bound by these functions right here, y equals negative x plus 4. Okay. We're going about the y-axis. So 1, 2, 3, 4. 1, 2, 3, 4. All right, so first off, negative x plus 4 is a function, it's a linear function with a y-intercept of 4 and a slope of negative 1. So down, start here at 0, 4, down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. So it's going to look as such. Okay. And y equals 1 is a horizontal line as such. And x equals 0. So what we have is this region right here. And we're revolving this about the y-axis. So basically we have a shape that's going to look like this. It's going to be an upside down cone. Okay. So we're going to be going from, we see here we're going from, in terms of our y values, we're going from 1 up to 1, 2, 3, 4, up to 4. Because remember, it has to be in terms of the y values. And it's going to be pi r squared. So I'm just going to go ahead, since we did that a couple times. So we're going from 1 to 4. I'm going to put this pi out here. Now I need the radius, but in terms of y. Okay, so we have to look at y equals negative x plus 4. And we're going to solve for x. So we bring the x over here, bring the y over here, so 4 minus y. So that's what our function y equals negative x plus 4 in terms of y values is going to be 4 minus y. So that's what our radius is going to be. All right. So it's pi r squared, so it's going to be 4 minus y, quantity squared dy. And once again, we have to FOIL this out. Which is going to be pi from 1 to 4. 16 minus 8y plus y squared dy. Okay? Or if you like to write it back in standard form, which is highest power first, descending y squared minus 8y plus 16 dy. That's perfectly fine. Okay? And so now we're going to take the antiderivative. Oops. Sorry about that. So it's going to be pi. And it's going to be 1/3 y cubed minus y squared. 8 over 2 is going to give us 4 plus 16y. And we're going from 1 to 4. Okay? So let's substitute in 4 first. So 1/3 4 cubed minus 4 times 4 squared plus 16 times 4 minus, and we got to plug in 1 now. 1/3 1 cubed minus 4 times 1 squared plus 16 times 1. And so that pi is still going to be out there. So 4 cubed is 64. So it's going to be 64 over 3 minus 16 times 4, which is minus 64 plus 64 minus 1/3 minus 4 plus 16, which is going to give us, now these cancel out, which is sweet. So we have pi times 64 over 3 minus 1/3, and that's going to be minus 12 or minus 36 over 3. Is that right? Let me make sure. Yep. And that's just distributing that negative. And so 63 minus, it's supposed to be 27 over 3, is that right? Minus 37, let's see. 63 minus 36 would be 27 over 3 pi, which is 9 pi. Nice. And that'll do us. All right, you have a good one, guys.